Hey folks, it's 10 a.m. Thanks a lot for joining us today. We've got a gaggle of folks from Price Industries. We'll go over their bios in just a second. As we're getting started, I just wanted to give you all a preview that we're going to be talking a lot about panels and ambient acoustics today for equipment and for ductwork. So in addition to this class that we're having today, we're putting out a road show in May. You can see the dates on your screen: May 12th in Milwaukee, May 13th in the Fox Valley, and May 14th in Madison. So we're going to have a little Sprinter van, and of course a food truck, because God knows we all got to have something to eat. But we're going to be demoing some of the equipment that you're going to see in this presentation today. And just to give you a little bit of a feel, one of the things, if you look closely at the picture, the kids are building a brick wall. We're going to have you build an acoustic panel enclosure, and then we're going to do some testing so you can get sort of the the sound and feel for assembling panels, how easy it is, and what an impact it has on sound. So without any further ado, I'm going to turn this over to three very capable people from Price Industries. That's Mauricio and Sadem and Jackson Popple. And I had a chance to preview all this information yesterday, and there's a lot of content, first of all. So you're not going to be want for material. If you would, please put your questions in the Q&A, and we're going to try to batch answer those. So Jackson's going to be standing by to answer. And we'll try to get to all of them at sort of our convenience so we get through all of our slides. So without any more preamble, I'm going to turn this over to Mauricio. And Sedem and Mauricio and Jackson, thanks for doing such a great job in prepping for this class. I think everybody's going to be really happy with it. So thank you. And let's go.
Thank you, Tom. Good morning, everyone. Thanks for attending today. My name is Mauricio Salinas. I am the Sales and Business Development Manager. I have to get used to saying it because it just changed. It's sort of new to me. I have been at Price for 14 years, and I oversee the sales and engineering teams for the noise control product line at Price.
Good morning, everyone. So my name is Sedem Kumaho. I am a technical sales engineer at Price Noise Control as well. Been with the company a little over 3 years, and yeah, specialize in silencers, acoustical panels, and doing acoustical analysis altogether.
I also like to say that we have Jackson answering questions, but it's also my backup. I'm expecting my fifth child anytime. So if for some reason my wife calls in the middle and you hear a beeping and the presenter changes to Jackson, now you know why.
Hi, I'm a technical sales specialist on the apps team as well. So I'll hop in if Marisa needs to leave.
Thank you, Jackson. You're a champion. To start with, over the agenda, we're gonna go over the approach, talk specifically about panels. We're gonna go over barrier walls. We're gonna touch on thermally broken panels and applications. We're gonna look at custom solutions, custom enclosures for chillers, emergency generators, and other solutions. So the approach that I like to call is always having the minimum level of understanding on how to approach any noise control or any noise issue by starting to identify your source and what you need from your source. So anytime you're dealing with a noise complaint, or before that, hopefully after all the guidelines we're going to give you, make sure that you select the source that's as quiet as possible. And for that, you're going to need 8 numbers. So whenever you try to address any noise control issue, you're going to need those 8 numbers. It's not enough to just have a single number rating, call Tom and say, hey, I have a fan that's 95 dBA single number rating. We want it at 60. We need the cut sheet of the source with the 8 numbers to see what frequencies are driving sound to properly attenuate it at the receiver. Second element to understand is your path. Is your path indoors, outdoors, what's on the way, and the distance to the receiver. What the receiver is. Is it a school? Is it a library? Is it a performance arts? Is it a gymnasium? Different spaces are going to have different requirements. Over the course of this session, this webinar, we're going to focus a lot on custom solutions, starting with how to size panels at the bottom of a curb. In many cases, you don't have enough isolation below, and it's just sheet metal with insulation below. As you can imagine, some of the frequency coming out of the unit, both at the if it's a bottom discharge curve, could be intrusive to the occupied space below. We're going to talk about barrier walls, surrounding barrier walls. We'll talk about custom enclosures. We're going to see what you could do to improve the acoustics within a room and add absorption to an occupied space, or also outdoors, the benefits of having perforated metal on an outdoor barrier wall, as well as applications for partition walls, including air handling unit casings and outsider plenums. To start with, the most common rating used to talk about sound levels at a particular distance to quantify it is the dBA or dBc level. So the A specifically is a way to describe how the human ear hears sound. In other words, we're applying correction factors to mimic human ear sensitivity. I'm going to explain specifically on the next few slides how that calculation is done. So whenever you're talking about meeting a particular noise ordinance at a residential building or a school, have in mind that if it's outdoors, you're going to have to use dBA or dBc. dBc is typically used for peak or impact sounds, or sounds that are so loud that could create instant or immediate hearing loss. So you'll see ratings for anything about 110, 120 decibels in airports, airplanes. All those will use the rating for C weighting, which means performance is not massaged to human ear sensitivity, because even though some frequencies may not appear as loud to us, they could be detrimental to human hearing. So to explain in detail how that looks like, I have the cut sheet of a mixed flow fan from a particular manufacturer. We're going to focus on radiated noise, but this could be done for the inlet sound power levels, discharge sound power levels for that particular fan. Now, just because we're focusing on radiated to talk about panels doesn't mean that you should not treat the discharge or inlet. The main message in this session is going to be the moment you treat one or the other is going to have an impact on the outlet sound power levels or radiated sound power levels. So just have that in mind. It's not just one path. You're going to have to treat all of them. Radiated path in a specific is going to be the sound that gets emitted through the casing of that fan into a particular line of sight at a certain distance. So LWA that you see in there, watts LW, that's sound power A weighted. So those correction factors to correct for human ear sensitivity are applied, and those are minus 26 decibels on the 63 hertz. So you're effectively taking 26 decibels, because to us, that 63 hertz doesn't sound as loud. The 125 takes minus 16 decibels, so on, all the way to adding a few decibels on the frequencies that we are most sensitive to. All in all, so that it gets logarithmically added to get that single number rating that you see at the end. So that's the dBA sound power, LWA. So these 8 numbers get quantified in a single number rating, which means this unit, when you plug it in, is radiating airborne noise at 53 decibels. Now, the second number that you see to the right on any cut sheet for equipment is pressure, whereas LW is power. The dBA that you see on the right is pressure. We hear pressure. The human ear, as a sound wave expressing your eardrum, that pressure is force over area to move your eardrum back and forth. What we hear is pressure. What you measure with a microphone is pressure. Now, when you read the small writing on the cut sheet, it's telling you that it's accounting for almost 12 decibels of reduction on each frequency to mimic 5 feet of distance. When you hear something, you have to be at a distance away to be able to measure that pressure. So looking at that calculation, almost 12 decibels, so 11.5 decibels on each frequency gets deducted. That gets logarithmically added to get the 42 dBA single number rating A weighted. So now you're experts, and anytime you see sound power levels on a piece of equipment on a cut sheet, you're going to know that LW is the sound power quantified in a single number, and the next number is how you're going to hear it, or occupancy is going to hear it at 5 feet. So the concept of intensity comes in handy to know for you guys is as if you picture a piece of equipment, in this case, the speaker, emitting sound equally. So it's radiating evenly in all directions in free field. The distance where you start measuring becomes the radius of that hemisphere. To calculate that area, you use the 4 pi by radius square to be able to see how a sound travels. That wave has to cover a larger area, meaning that as the distance grows, so the further away the receiver is, the wave has to spread thinner, meaning there is less of a wave pressing against a larger area. So intensity decreases based on distance. Using the formula of power over area, which is intensity watts per meter square, as an example, if we have in an example your radius or distance being 2 meters, and we measure, we know that the unit is emitting 1 watt, just for simplicity, as an example, and then we make the calculation of intensity now by squaring the larger distance, so 4 meters, you'll see that your intensity has greatly been reduced over that area. So transferring that into the relationship from intensity to pressure and try to quantify that in decibels, because that's what decibels do. They are quantifying the spike in sound pressure from the lowest possible we could hear, which is 20 micropascals, to above that, which is 20 pascals or greater. When you look at the formula, just to not make this extremely long, and plug in the intensity on this formula to your reference intensity, which is the lowest intensity the human ear can hear, you'll see that when you're doubling that distance, you have a 6 decibel increase. So that comes from that inverse square law. All in all, just to give you a quick rule of thumb, use your distance to your advantage. If you have a unit that you are replacing because somebody complained, and you measure that to be, 42 decibels is pretty low at 5 feet, but in this case, it could be louder. Don't replace the new unit that can be quieter in the same spot. Maybe put it at least double the distance where it was before, so that you get an extra 6 decibels. Now I'm going to ask you a question. If we measured 42 dBA single number rating without using all those crazy formulas that I showed you in the previous slide, what would be the sound pressure at 10 feet in free field? You could type it in the chat. All right, if you were paying attention, you get an extra 6 decibels per doubling of distance. That would be a 36 dBA, which in case, if you were to think about this mixed flow fan, perhaps close to a parking lot right outside of a school by a window, where the design goal of inside a classroom is 35 dBA for a high learning space, doubling the distance without using an enclosure, for example, would give you the 35 dBA when they open the window in that classroom. So message is, use your distances to your advantage. A couple other pieces of theory to remember as it relates to sound, specifically on perception and sound addition, is the human ear cannot perceive any changes lower than 3 decibels. So doubling of power is a 3 decibel spike. So what that tells you is we need the power to double for us to be able to sense that change. However, to us, a 3 decibel increase is not perceived as twice as loud. A 10 decibel increase is what we perceive as twice as loud, or a 10 decibel reduction is half as loud. So out of this slide, for you, for simplicity, the takeaway is to remember the number 3 and the number 10. The number 3 is when you double of power. That means you increase by 3 decibels. And the 10 decibel is good to remember when you're looking at sound levels at a particular point, whether it's ducted or unducted, and you're looking at a different source. If the difference between these two sources, let's say you have a fan at 70 decibels and one at 90, the difference between them is greater than 10, you're only going to hear the 90 decibel unit. So in other words, even when you look at self-generated noise by other pieces of equipment or look at the added sound power levels of a single duct valve in the duct, as long as those sound power levels are 10 decibel lower than what's remaining in the system, you are not adding noise to the system. So remember, the number 10 it's handy. So if you have two fans at 70 decibels each, the resultant value is going to be 73. And that can be related to exposure levels based on OSHA or NIOSH or based on the many regulations out there, both for the US and Canada. You could use those rules to see what the exposure limit should be. So the maximum allowable noise exposure is 85 decibels outdoors for 8 hours. When you use that number 3, which is doubling of power, let's say you have now 2 fans, and then you have 6 fans, and you start adding noise by 3 decibels, your exposure time gets cut by half. Very quickly, you can notice that whenever you're getting closer or above 100 decibels, you could induce permanent hearing damage to the human ear pretty quickly. So remember that. Anytime you see equipment that has really loud sound levels exceeding 110 decibels, likely you will need some sort of noise control treatment to get acceptable sound levels at a certain line of sight, but also to not damage the public. The image in front of you is the typical description of a problem. It could be a big mall, it could be a massive building with several fans. In this case, it's a data center. But when you look at this right here, you have hundreds of fans.
For whatever reason, Mauricio, it's really dark, so maybe you can describe it. It's just in this picture. It's really
Oh, the
hard to
picture
see.
is super dark.
It's really dark.
That's strange. So we
It's
cannot.
a community next to a factory. It's hard to tell. It looks like more
Okay.
of a model.
Well, thank you. I'm surprised. It looks very clear, but yes, you have
Are you
hundreds and
surprised
hundreds
I'm
of.
paying attention? Or are you surprised that the picture's dark?
I'm surprised that the picture is dark because we sort of looked at this before. We try to prep as much
Yeah,
as we
we
can,
looked at
but
it yesterday. It was clear as day. So
yeah. So in other words, for the audience, apologies for the bad visuals. We're an acoustical team. We're not so focused on the visuals. But if you were to picture the scenario is you have hundreds and hundreds of oblast fans within 500 feet of residential, and that right away is a quick key for you to know that you're going to need some sort of treatment. Most of the complaints come from high learning spaces and residential, especially when people are trying to sleep. And the equipment kicks in to cool off those servers, and you have hundreds of them at 90 plus decibels, you're going to have a problem. So moving on to acoustical panels now, we're going to start talking about the different sound paths from structure-borne, which you treat with your typical different types of isolators from neoprene pads to true spring isolators. In this specific session, we're mostly going to focus on airborne path or ductborne path. Specifically, a reminder, and this is a good infographic here that shows you if I were to add a silencer on the discharge here on the duct coming from the top, that is going to block some of the airflow. The silencer inside is meant to impede some of the waves, lower frequency waves from passing through, and the waves that pass through, they get absorbed by means of friction and changing your sound and energy into heat and kinetic energy through vibrations. But by obstructing the airflow, you're going to create back pressure to the fan. So what happens to your radiated noise when the fan ramps up? Your radiated noise is going to increase, aka exposed applications. You have fan power boxes in a space with all of a sudden you add inlet silencers and discharge silencers, and you still have noise complaints. Well, that's because you are increasing 2 to 3 decibel single number rating your radiated noise. And for that, you add mass. You have to add an enclosure or a ceiling or a cloud ceiling with enough transmission loss to get to a certain sound level in the space. What we typically use to address that radiated sound is wall mount panels, double wall panels, which will have a rating for STC on NRC, and we're going to talk about what that means. What they'll do is block and absorb sound, and the two different types of designs that we have are tongue and groove and H-clip options. So depending on the size, Depending on the style and thickness of the panel, you could get a tongue and groove, which minimizes the amount of screws at the joint. Typically, you just need one at the top and two at the bottom, and no other screws at the joint. So the tongue and groove panel is very appealing to a contractor because it saves you about 25% in labor installation by not having to fasten or add a lot of screws through the joint. The first piece of terminology as it relates to performance is sound transmission class. That's the ability of a building element to block sound. It's tested under ASTM E90. And in other words, what it does is you have two reverberant chambers. One is throwing sound levels equally on all frequencies, and we measure through a hole and a partition wall to see how much it transferred through without a wall or panel or louver. And then we insert the test specimen in that 4x4 opening, and we measure how much it transmitted through. We measure that difference. So that is the ability to block. So something that's very wide with a lot of density is going to do a very good job at blocking sound from transmitting through. An example of using sound transmission class in an application could be at the bottom of a vibration isolation curve. A lot of the times, the bottom of the curve, especially when it's bottom discharge, not so much when it's side discharge, gets overlooked. You don't have concrete decking below, and all of a sudden, you're dealing with a retrofit application, and the unit has to sit right above a meeting room, a classroom. Close attention needs to be paid out when you're looking at such a scenario. We have different examples of building elements with different sound transmission classes, from a piece of general ceiling tile, half-inch drywall, and comparing that to a 6-inch concrete slab. If you think about how thick that is and how dense it is, obviously it's going to give you a lot of attenuation of all frequencies, including low frequency noise. As a general reminder for those who have dealt with acoustics, and even if you haven't, the hardest frequencies to attenuate are going to be these first three because of the size of their wavelength. The size of the wavelength of the 63 hertz is 18 foot wide. The size of the 125 hertz is 9 foot wide, so on. So therefore, you're going to need something very thick to be able to do any attenuation at those. So in general, if you were to have the scenario that I showed you before, using an STC57 double wall 4-inch panel with 16 gauge construction on both sides and in mineral wool internally with 5/8 gypsum board would give you close to a single number rating of 48 decibels overall. Now, have in mind that just because we say, hey, this is STC 50, it doesn't mean that it's taking 50 decibels on each frequency. As you could tell, it's giving you less frequency, less performance on the lower frequencies, and then the average reduction is going to be about 48 by doing that. So the combination of the treatment at the bottom or the isolation building element you have on the roof plus your ceiling type is going to give you it's going to get you the resulting sound level from either 50 decibels by just using the typical 20 gauge with 2-inch liner floor at the curb. You could get around 57 to 60 decibels in a learning space that's not acceptable, or you could go all the way to an STC 57 panel with general ceiling tile, also in the space that will get you to 34 dBA, which is acceptable in a classroom because the max is 35 dBA. So just an example on where STC can come in handy for noise isolation. Now, the other piece of terminology is noise reduction coefficients, NRC, tested under ASTM C23, and that is the property of a building element to absorb sound. And typically, when you use this, is for the right acoustics in the space to reduce the reverberation time within the room. So a soft, puffy material like a pillow. Pillows are very good at keeping people quiet for good. I don't know if you've seen those movies where they use them for sound specifically, or a very reflective surface.
Those are really good for keeping people quiet for good.
Correct. And something as reflective as concrete or glass is going to be fully reflective, so the NRC is going to be 0. The way you would use these ratings in reality is mostly for indoor acoustics. It's more of an architectural feature. However, it comes very handy because if you are doing a barrier wall outside or an enclosure, you could amplify sound and reflect sound back if you don't have absorption towards the source, adding 3 to 5 decibels to the irradiated sound by reflecting that sound back. So have in mind that having at least the surface of your barrier wall being perforated is gonna prevent sound amplification. But if you are dealing with any of these indoors, when you want to add absorption to the room to get the right reverberation time, typically, especially in multi-purpose spaces, when you want to have a gymnasium and all of a sudden use it once in a while to give speeches or teaching, you're going to have to add a lot of absorption on the walls so that you could get less than a second reverberation time. So for speech intelligibility, you want to reach at least a maximum of a second for 60 decibels to dissipate in air. So just have that in mind. Absorption coefficients are also something that you could specify as you're doing an outdoor barrier or indoor absorptive panels. So that is the performance you're going to see on double wall panels, either of 2, 4, 6 inches up to 8 inches that we can manufacture as custom. And when you look at the absorption, which is a function of the thickness of the frequency and the wavelength of sound, you're going to get a lot of absorption the thicker and softer your material is. We classify these solutions based on different types of panels between type 1 and 2, which is outdoor barriers with an open top. We also use a lot of double wall solutions with type 3, which is acoustical plenums, whether it's an outside air mixing box or an exhaust box behind the louver, or through enclosures for just sound booths or chiller enclosures, generator enclosures, where you might have to have openings for ventilation. Starting with, we're going to talk about outdoor barrier walls, and just brace yourself because you're going to go in for a good 2 hours of content. So make sure you ask questions and type them for Jackson to answer. But if sound waves did not bend, which they do, barrier walls would be the ideal isolators. But because of diffraction and sound, those waves bending over, you have to really pay attention to the distance to the receiver and have parameters to size the right height of your barrier wall. So some of the sound is going to be what gets transmitted through, and some of it is going to be what goes over and down to the receiver. So that is typically governed by doing a path length difference equation. So the longer the path length, the more attenuation you're going to have. You could go back and try to review all your trigonometry, or you could use the formula that I'm showing you here on the right. But as you could tell, if your path length difference by making the height of your barrier very tall and as close as possible to the receiver, relative to the source height and the receiver height, the taller your source is, obviously, your taller your wall is going to be, and likewise with the receiver. Notice that we are using a table with already calculated insertion losses for, or a decibel reduction on each frequency for the barrier wall at different path lengths. The longer the path length, the more attenuation you're going to have on each frequency. Note that the maximum performance you could get on either frequency is going to be 24 decibels. So you cannot get more than that. When you're dealing with chillers, for example, you have to have at least a 3, 4. If you have 2 of them side to side, you have to have at least 6 feet of distance between the source and the receiver, meaning that your wall is going to start requiring to be very tall. For practical purposes, the maximum performance in one shot, single number rating average that you could get from a barrier wall is going to be 10 to 15 decibels. So when do you need when do you know you need an enclosure? Is when you need more than 10 to 15 points off your sound source to get to your 45 dBA when somebody's trying to sleep, or 35 dBA in a window of a classroom. Now, most of these barriers are surrounding barriers, so making a full 4-sided wall around the source, or at least a 3-sided one, because if you just use a single barrier, that barrier has to be at least on each end relative to the unit 3 times the path length difference from the source. So you all of a sudden you have a massive extra long wall that it's a lot easier and cost effective to do a full surrounding barrier. So effectively you're trying to create a shadow zone so that waves have to go up, over, and bend by diffraction and decrease that sound level, making them travel a lot further than they would otherwise in a direct line of sight. Thankfully, there are tools from us or from other manufacturers that allow you to size that height of the barrier effectively. In this specific case, the minimum pieces of information you will need is the distance of the wall to the source. In this case, is 4 feet. The distance to the receiver, where is the line of sight? It could be a window 20 feet away. Your source height, so this specific radiated air handling unit or rooftop unit, it has 8 numbers. Remember those frequencies here. You have the loudest at 125 hertz. I'm gonna need those 8 numbers. And in this case, you're saying that there is a window or someone standing outside at 6 foot tall at the ear level. Calculating now, telling you that you at least need a 12-foot barrier wall, so 2 feet taller than the unit to get in combination with distance. So the 20 feet in free field by inverse square law, the formula that I showed you at the beginning, in combination with distance, you could get from 72 dBA to 59 dBA during the day. So if all of a sudden it is indeed a window in a classroom, then 60 dBA is too loud, aka you're going to need a full enclosure on that unit. These are some examples on barrier walls. They are not as simple as just putting them out there and then add on the specification. It needs to be self-supported. They're exposed. They're going to be exposed to wind loads. They're going to be exposed to seismic. And depending on the height of the room, a particular wind loads is going to be applied. So they come with structural requirements as well, and protection to the elements. In this case, you could see these barrier walls outside of a data center are fully powder coated with absorptive perforated metal on the side facing the source.
Hey, Mauricio, quick question for you. For the requests that the department receives, and this is just going to be a guess, but are most of your requests in the planning stage where you're going to build a facility and they know they need a barrier wall, or is the lion's share of your requests, oh man, we've got a problem, what are we going to do?
I could say the majority is after the fact when there is already an issue, which
Okay.
means it's going to be a lot more expensive because of the structural requirements to fully support the treatment. Now, because of good reps like your office and a lot of good engineers being more aware of this, there is
Oh,
a lot
shut.
more. There is a lot more awareness of around sound ordinance. So it's trickling down typically from the west in Seattle, where all the acoustical pioneers are, and then all those guidelines trickle down towards the north and in the east of the U.S. But in general, over time, and if you look at the third biggest chronic disease in the U.S. is hearing loss, so it's gaining some momentum. So hopefully we can change that, and all of these can be looked at the design stage, which is it's a good comment, Tom, because that's sort of the main topic. There is a good way to do this, and it's the cheapest at the design stage. Another example is this bakery in Atlanta. We also sized that barrier wall, including absorptive panels at the back wall so that sound didn't go and reflect and over, including some localized barriers or discharge plenum barriers for the condensing units at the top to make sure that the residents, are within 50 feet from this, because they had to put all the equipment on ground level facing homes, weren't complaining. So all that was done at actually, this was after the fact when they had to put the equipment. However, the fact that we had access and they could pour a new concrete pad made it a smooth process. You could be in residential areas with equipment and all of a sudden near schools as well on the right. So the thickness and the robustness of your solution is going to be based on distance. So use your distance to your advantage. In this case, a solid wall with perforated metal was enough to give the 5 to 8 decibel reduction nearby so that they could avoid any complaints moving forward. So again, sadly, a lot of the case studies I'm going to show you are complaints after the fact. I'm hoping that one day, and I do have one on the go where I'm doing it at the design stage, but it'd be good to finally have one where we just showcase how we didn't get in trouble. Now I'm going to take a little bit of a break from talking so much and hand it over to Serem. Serem is going to talk about thermally broken panels.
Thank you, Mauricio. And hi, everyone, once again. We would be discussing the science behind thermally broken panels, condensation on outside air, plenums as well. Let's do some heat transfer basics. What direction would we typically have heat transfer? It would typically be from the warm side to the cold side. That's super important to understanding everything else that we're going to discuss. So heat would always flow from the warm side to the heat side. We've always had an R value. R value is the temperature difference required across a material to drive a certain rate of heat flow. That really is the fancy way of saying it, but in reality, it's just a measure of the material's resistance to heat flow. So the higher the R value, the better the insulation. The R value of any material, any assembly would be dependent on the material thickness and the thermal conductivity. So if you have a thicker wall, a thicker panel, you should have a better R value. And if you have insulating material with a much lower thermal conductivity, you should have a better R value. This is all to say that the higher the R value, the lower or the less the heat transfer. And the lower the R value, the more the heat transfer. But this is an inverse relation, and it's typically harder to recall. So they came up with a new concept called the heat transfer coefficient U, which is what we typically work with in the industry. The heat transfer coefficient is the inverse to the R value and would give us the relation: the lower your U value, the less the heat transfer, and the higher your U value, the more the heat transfer. So if you have thermal applications, your goal would be to have a specification where you have a much lower U value for your assembly. And let's look at typical panel constructions as they relate to our acoustic panels. You typically see a U factor of 0.1 for 2-inch panels, 0.06 and 0.05. These are for our competitor. Well, these values are based on the insulating media only. For a typical mineral wool, the R value is 4.1 per inch. Once you multiply that for 4 inches and you do the math, you do have 0.06. So a single panel based off of the insulation alone would give you the 0.06, which you typically see in your specs. However, the overall assemblies would be much, much lower due to connections to structural and through metal connections. Why is it super important? In the winter, when you have outside air coming into your plenum or your duct, and you have that interfacing with warm air in your mechanical room, your warm air would carry more moisture in that regard since it is warm. Here's the scenario. Incoming air is fairly cold, -15 to 20, and you have your warm indoor space that's around 70. This could be an air-conditioned space, your mechanical room, or simply just a walkway or a pathway or a hallway in a space. What would happen is that if the surface temperature right in the warm indoor space is lower than the dew point of the air within that conditioned space, you would have condensation. This is super important. Once the temperature at the surface is lower than the dew point of the surrounding air, you'd begin to have sweating or condensation on that. What the U value does is that it helps to maintain the temperature on the outside to be much higher than the dew point to prevent condensation. So this shows us that the dew point is important in characterizing how or when condensation is going to occur. To specify this, we need to know what the relative humidity would be in the space. We need to know either the wet bulb temperature or the dry bulb temperature to fully specify this. The temperature at the surface would also be impacted if you have insufficient thermal transfer, right? So if you have a high thermal transfer right at your joints, or you do not have enough packing of the insulation in the panels, you would have a lower temperature at those locations. And if you have some air leakage as well, that would also lead to a much lower surface temperature that would eventually lead to condensation. Here's a practical picture of what the issue is. Right here at the corner of this door, through the frame, you do have the surface temperature being much lower than the dew point. So you do have sweating or condensation right at this point. This, yeah, might not be the biggest issue just because it's a little bit of water, but once you begin to have more extreme cases where you have ice buildup around the joints, this becomes very concerning. You have the expansion of water through ice, and then you could have the derating of your connections. If these plenums are pressurized, you could likely have the possibility of failure at these connections and it could collapse. If we know all of this, how are we trying to solve this issue? Well, this is a decent attempt at a panel spec. First off is specifying what the thickness should be. It is nice, it is thick. We're trying to make sure we have a low enough R value, so we could have, sorry, a high enough R value so we could have a low enough U value. They do specify what the insulation should be, and they do specify what the outside air temperature should be. However, we do not have any information on what the inside or the warm side temperature would be. If we know what the relative humidity is and the dry bulb temperature is, then we could begin to estimate if our standard panels would condensate if these are built. Another part that is fairly overlooked would be the doors. We do not think much about it, but the framing on the doors would lead to a derate on the thermal conductivity or the heat transfer through the door frame as well, and that could lead to condensation. Based on this, we did ask for panel specs for typical operating conditions, and this is what it came up to. We're given dry bulb temperatures, which were great. We have the cold side temperatures, which were great, and we also have the relative humidities. Now, with this information, we are able to estimate what the dew point temperatures would be. So once again, if our surface temperature is above that, no condensation. Immediately the surface temperature drops below that, we would have condensation. One thing we did note on this spec is for the most extreme case, which would be in the winter, we did see that they're specifying a 60% relative humidity within the warm space or the conditioned space, which is very, very high. Based on research and recommendations out there, relative humidity would be within 30 to 35% in the winter and just at maximum at 50% in the summer. So we would default this back to 35% within the recommended limits just to test if our panels would work in a typical real world scenario.
I want to just hop in real quick. The reason that SEDEM is putting this information out there is because, well, so we've, as a rep, and I'm sure SEDEM and Mauricio and Jackson see panel specs all the time. I've never actually seen one that had a performance that was based on the entire assembly. So when you're asking for a 4-inch panel and your assumption is, well, this is an outside air plenum, I'm fine. The truth of the matter is nobody really has done a decent job of articulating this, whether that's any of the competitors that build or a contractor that builds double wall panels, which is not that hard to do. We need to be more clear about what the panel itself does, but more importantly, what the entire assembly does. Because when you put a bunch of bolts through it, it's not what you thought it was when you specified it in the beginning.
Thanks, Tom. Tom literally just went right straight to my next slide. So to Tom's point, we always need to look at this as an entire plenum. Just looking at a single panel and what that value would do, which is really based on just the insulation, is not the right way to go about this. You need to look at all the through metal connections, all your connections to structural. Once you begin to have pressurized plenums, you need to be able to look at how these would connect to the structural frame to ensure that these are robust and meet the structural or the pressure ratings for that region or that setup. We're going to discuss a couple solutions. The first solution would be installing FSK, an FSK layer onto the cold side of your plenum. Now imagine you have a 30-foot plenum that's 20 feet tall. This is going to be a lot of work for your installing contractors. You have about 3.5 inches of FSK that has to be glued on all sides of your plenum. That is a lot of work. Well, it would work. CFD shows that with installing this on your cold side, you do keep your warm side above the dew point. The dew point here would be 41 degrees Fahrenheit, and the warm side is currently at 70 degrees. So there would be no condensation on this particular system. It would, however, be very expensive. If you also think of critical environments where having exposed fiberglass is not recommended or is not approved, then you begin to run into issues where you're not able to apply this FSK to that system. The second solution is what we have under development at the moment, which would be a thermally broken acoustical panels. This has a thermal break that bridges the gap between the warm side and the cold side. Unfortunately, still undergoing testing, so it has to be super confidential and top secret. I don't want to be the guy that gets a call from legal about this. If you look at the connections in here, we do have the thermal break where you no longer have the through metal connections, even with your screws, because these remain separate from each other right at the connections. You would always have your outside or your warm side being separate from your cold side. Let's look at some real numbers with relation to using the thermally broken versus our competitors' standard panels and the results that we've started seeing. For a standard supply duct, you do have your warm side around 91, that's heated warm air. And you do have your cold side around 50. This is typical as we see it. Your dew point would be at 66.9. Well, the standard panel would have a surface temperature at 75, which is above that, so there'll be no condensation. Thermally broken obviously would be a superior product with a much higher surface temperature. Once you have a look at your outside air plenum, you do have much colder air coming in. And with a relative humidity of 30 degrees, you also do have a dew point of 37 degrees Fahrenheit. The standard panel, again, does a good job at that point because it is about 7 degrees above the dew point, so there is no condensation. The thermally broken still does an excellent job in this. So no condensation so far, and we are all happy. But once you begin to have your much colder, frigid conditions during the winter, where you have minus 15 cold air coming in at 35 degrees relative humidity, you do have a dew point at 41 degrees. Now, your standard panel would have a surface temperature that is much lower than the 41. So you would have or experience condensation in this regard. No one is going to be happy with that if this begins to ice up and begin to cause issues on the site. However, the thermally broken remains around 9 degrees Fahrenheit above that dew point temperature. So this makes it much, much more superior when it comes to handling colder climates and your outside air plenums. So why are we saying all of this? The thermal break reduces the risk of condensation. It ensures that there's a uniform flow of temperature across, and we can make sure that we avoid scenarios where we have condensation. This would be the only true thermally broken panel that is being developed on the market. And as always, do not forget the doors. Price actually does provide thermally broken doors as well. For now, all we would say is that at a temperature differential of 85 degrees and a relative humidity lower than 50%, we should be hitting this target. So I guess all our competitors might be looking at us like, wow, this should be a great product. Now, this is why it's super important. On very large outside air plenums like this one, where you have a 17-foot tall plenum and it's 30 feet wide, this is going to need additional stiffening. You're going to have a ton of connections, structural steel, exposed metal all through this. If you do have very cold air at minus 15 degrees coming in within your space, you are going to have a lot of condensation on all the connections that you do have, which is where the thermally broken panel becomes the superior product. This is what it would typically look like with all the connections, all the panel layouts, all the thermal bridges through it as well. And we really want to make sure that all these connections are taken care of and considered carefully. This is a typical spec that I would like to bring to light as to what we typically see when it comes to getting specs around thermal breaks. And The first thing you want to look here is the thermal performance. Here it says individual panels shall have a heat transfer factor U of not more than 0.06. In reality, this would be only the insulation. This is what the insulation is providing at 4 inches of a panel. The entire assembly is not doing this unless you have them truly thermally broken. Next thing you see here is that it has to be designed to 10 inches of water gauge, which is very, very high. So would require robust structural stiffening. With structural engineering, this is what that plenum came up to with all the structural connections. We do have all the drawings, which we are able to design with the help of an external structural engineer through price. We have all the details, we have all the connections, and if you have something of this nature and you need to ensure there isn't condensation, then you need to make sure that you are taking care of what the warm side conditions would be, what the cold side conditions would be, and we would need to analyze that to make sure that you need or do not need the thermally broken panels. If there's a risk of condensation, then we would provide the thermally broken panels for that application. Next thing we want to discuss would be using our panels, our acoustic panels, as ductwork. Most of the ductwork would be based on SMACNA guidelines. Looking here, if you have, say, a 120-inch wide duct, if you wanted to make sure this hits the 6-inch positive or negative pressure, we do need to make sure we are reinforcing this every 2.5 feet or every 2 feet. Anything that has any wider spacing is not designed yet. How would we keep that? We want to make sure that we are having wider stiffener spacing, so we are having less obstruction to the airflow that's coming in, and we have a higher free area to ensure that there's less turbulence, there's less pressure drop in the system, and yeah, you would be able to make sure that all your systems are running as expected. Well, to do that with the SMACNA guidelines, you're going to need tie rods. And with tie rods means you are bridging all the thermal connections, and this would mean that your U value derates and becomes much higher, and you could still risk the possibility of condensation on those. This is a snippet that I included for a 48-inch wide duct. If you wanted to meet the 6-inch pressure rating, you would need a tie rod that could, you know what, for a spacing of 4 feet, for reinforcement, you need a tie rod that could withstand up to 372 pounds of force or load on that. If you wanted to increase that spacing to 6 feet, you need a much bigger tie rod that can withstand 564 pounds. Once you begin to have all of these every 6 feet, you're beginning to run into issues. I don't want to think of what you would have to do if you have a 120-inch wide duct. This is fairly common as we have much, much larger or wider supply ductwork that we deal with. I do have an example here that you could see. This is a supply duct connections. These are ductwork that they needed to run through on a roof. As you can see, after structural design, we do have 8 feet of spacing between the posts that are required to ensure this meets the structural performance or the integrity at 6 inches of water gauge. This is much, much wider and would provide less obstructions compared to what you would have for using the SMACNA guidelines. So we always recommend that once you begin to have much larger ductwork, you should begin to consider what our panels could do for you in that regard. This is also another example of supply ductwork that is present on a roof where they need to move a ton of air through various spaces. If you look at the dimensions, we have 168 inches wide. We can do this in one single panel to be able to make sure that you have the highest free area available. If you look at the width as well, this is as long as 828 inches wide, which is a wide span. Now, on this particular job, we do have the 168 inches span, but our HSS tubes are spanning only 6 feet and running only along the center just to make sure that they are carrying the weight of this top panel. This would ensure that we are meeting both the positive and negative pressure ratings that these are designed for. And this is designed up to 10 inches of water gauge. So to conclude this, we're saying that with using our acoustic panels for ductwork, You could minimize the structural steel required. You could ensure that you have the optimal free area and reduce the turbulence and pressure drop within the system. A 2-inch panel should do good up to 4 inches of water gauge, and the 4-inch panels we typically use for up to 10 inches of water gauge. I'll pass it back to Mauricio.
Thank you, Serem. Very well done. Hopefully that was informative to everybody. When you're trying to support those plenums, the more you have on the way, additional to what Serem mentioned by, basically removing your thermal break and obstructing noise. When you obstruct noise, then you're going to create noise. When you obstruct airflow, you're going to create noise. So the least amount of obstruction in the airflow, the better overall as a solution. Moving on, we're going to talk about chillers now, some of the solutions that we use for that. And what we use is tested data, and what we use is noise control products derived with tested data that's accurate. So that is the main message of this slide. Whenever you're now having to provide openings on an enclosure, in this case on a chiller for the exhaust at the top or on the compressor side at the bottom, then you need to maintain the transmission loss of that enclosure. And how do you maintain that? Well, you add silencers, and what silencers do is they are going to allow for airflow to go through while also offering sound reduction as waves pass through them. Now, the latest standard as it relates to silencer is ASTM E477-20. Yes, you could write that down. That is the most accurate set of performance as you are laying out a specification and you need silencers, whether they are ducted or unducted for outdoor solutions. You want to make sure it's up to the latest standard. What that means is if you look at the graph in front of you, the raw tested data on each frequency, for example, on the 63 hertz, we're taking 4 decibels off. On the 125, we're taking 5 decibels off. The most amount of performance on this specific tested unit, which is a 36-inch long 24 by 24 silencer, is at the 500 hertz. You have about 18 decibels off. Now, you test that in a lab with very accurate equipment. And in the past, due to reproducibility means trying to reproduce the same results in different labs had a difference in performance. So the standard and the body of the standard used to believe the information they were presented with, to the point that the same silencer with the same materials, and even though the way sound travels inside ductwork hasn't changed for almost 100 years, it has never changed since it was quantified and discovered, it should not have that crazy of a gap. So all of a sudden, for 2 silencers of the same geometry, same free area, manufacturer A could give you up to 16 decibels of performance higher than manufacturer B and C. Why was that? Well, the tolerances were a lot more flexible. So you could test on the black line and somebody could massage levels to the top of the light orange area. Acoustical consultants and engineers got tired of this. It's a bit of a mess out there in the industry for noise control performance. So we offer our state-of-the-art laboratory. We tested the silencers from all the competitors out there, at least the ones who wanted to, that were smart enough to participate in the round-robin testing. And so we got the performance for them, and not just the one geometry, different geometries and different lengths. And when you look at that, the performance is within 1 to 2 decibels between each other. We also send testing specimens to Intertech, which is the light bluish or gray, depending on your screen, just so that competitors wouldn't say we were biased and the price was, manipulating performance. So you could even tell that it is almost within 1 to a half a decibel from our tested raw data. So very accurate. So the takeaway on this slide for you is just to specify under the right standard would ensure that massaging on performance doesn't occur. So when you look at the limits on their ASTM E477, which is the dark orange, manufacturers cannot modify performance more than a couple decibels, which lines up with human sensitivity pressure changes. A change in performance that was 1 to 3 decibels is not going to be sensed by the human ear. Any manipulation of performance that's larger than that could impact in louder sound pressure levels in the space, especially if you're trying to treat heavy equipment. If all of a sudden your silencer doesn't do what it told you it was going to do, you could have some liability on the solution. In front of you, you have a typical specification that's becoming more common, especially when you're close to schools. In this case, you'll see that the nighttime maximum sound level is 55 dBl close to residential. And at the school, because this was right on a schoolyard, it's 35 dBA. So you have a unit that's at 90 decibels to get it to 35. You're going to need a big enclosure for that. Additional to that, you have to account for spacing. You cannot put anything in front of these units. Traditionally, the rule is do not obstruct airflow into a chiller or you're going to impact performance. Typically, as long as you keep a barrier wall 3 feet away for a single chiller, that is acceptable by most manufacturers. And now, don't forget, you have to also account for the environment. If you're close to the coast, likely you're going to have to powder coat or you're going to have to use 304 or 316 stainless steel. So in this specific example, I do have a video to show. I think most of you have seen it. It's a project in Reston, Virginia for the Reston Library project. So we replaced this old chiller in here and upgraded that masonry brick barrier wall to a true enclosure. Mainly because they have a library on the left and residential buildings on the right. So here you have an example of the submittal, and you'll see that we have very large openings and no openings on the sections or on the paths where you have a direct line of sight, allowing for access for the coil. So these access doors at the back would line up specifically with the V coil so that they could remove them without having to take the entire enclosure, along with a fully removable silencer bank at the top. In the case they need to replace that chiller, then they can take the lid off, put the new chiller in without having to size a new enclosure. We did the CFD analysis as well as a minimum, you need this is the top of the chiller, just so that you guys know. It's just tilted sideways on this specific analysis when we were looking at the back pressure created by putting silencers too close to the fan. So the orange is the back pressure that we create on that plenum, and it's the amount of pressure the fans are going to have to overcome to push the air out. So using the right silencer with the lowest pressure drop, a very specific distance away, which for a discharge side on a chiller is at least 2 feet of distance between the silencers and the fans, can ensure that you have acceptable pressure drop levels as per manufacturer of the chiller recommendations. We can do the structural support as well, but rather than me talking about it and in slides, I'm going to show you a video of the solution on this, and we can conclude the approach on chillers and talk about more examples after. Now, additional to that, they did use ultra quiet fans on top of using fans that could account for the back pressure added to the system. So another example of why looking at this at the design stage is key. Additional to this, just for research purposes, or also because it was a requirement by the owners of the library and as requested by the residents behind, where you see a lot of balconies, we did a site survey. And just to kind of reiterate the importance of using tested data to get to accurate results, I did go and measure after the fact on several points 5 feet away to corroborate that my prediction of 55 decibel single number rating sound pressure was indeed what they achieved. When I grabbed this theoretical calculation, and this is just a simplified version of it, it doesn't have the individual paths. When I measure inside, I was able to measure 53 dBA. So now ensuring that they met the design goal. A similar example on a job that we did, Jackson was the leader on this one, but instead of having slides to show you what was done, we also have a case study video to show you the approach on this chiller enclosure as well.
A Calgary Housing Corporation building was found to be in violation of local noise bylaws. Excessive noise from its air conditioner condenser, situated near residential and public spaces, made this a critical issue to address. The city initially planned to mitigate the noise by purchasing and relocating new condensers, but noise levels would remain a problem. A solution was developed to resolve the matter, ensuring compliance with Calgary's noise ordinance of 65 dBA during the day. The Price Noise Control Team successfully designed a solution that significantly reduced noise levels. The team designed and implemented a Price Noise Control acoustic enclosure that consisted of a structural steel package, 2-inch and 4-inch thick acoustical panels, QA645, acoustical louvers, RH silencers, and an acoustical access door. 4 weeks after installation, the Price Noise Control Team conducted a site survey to verify the results predicted by the Price Acoustic Analysis software. The testing showed the solution's sound levels at 55 dBA, measured 3 feet from the enclosure, with units running at 100% load during the day. This project shows Price Noise Control's expertise in delivering science-driven noise control solutions, demonstrating the value of working with a reputable manufacturer.
All right, so just to recap that was another after the fact solution, which means they have to open up the roof, reinforce it to be able to erect the enclosure. So at the very least, if this was done at the design stage, the bones below could account for a future load, saving time and efforts by all the parties involved, from the owner, engineer, and contractor ultimately. So moving on now to emergency generators. This is a new set of slides that I wanted to show you guys, mainly to bring awareness to the impact these pieces of equipment can have. Why? Because they are easily the loudest pieces of equipment in any commercial building, or in many of the buildings out there, as they are code mandated to have on most of these buildings to have backup power. NFPA 110 is the code that establishes requirements for performance on these generators, but as it relates to noise control, it sets the minimum testing frequency for these units. So in any schools, you have emergency generators, airports, police facilities, military facilities, and when you turn them on for testing, they can be extremely detrimental to human hearing. Although the minimum requirements for testing frequency under NFPA 110 is only to test them once a month for 30 minutes at available load, depending on the jurisdiction and the environment, these are tested a lot more often than just that. And you may think, well, even if it's just the minimum, who cares? They just cover their ears for 30 minutes. What's the worst that could happen? Well, in many jurisdictions such as California, Texas, Florida, a lot of, because of obvious reasons in front of you, whether you're in a hurricane area or you have harsh, environments such as yours with a lot of cold temperatures, a lot of freezing temperatures. And if you lose power, you want to make sure that those backup generators kick in. A lot of these units are tested up to twice a week for half an hour. And the reason, and this is important to have into account, is when you're emitting sound at 120 decibels plus from these pieces of equipment, you could generate hearing loss, permanent hearing damage in less than a minute. And that is extremely dangerous. You could open yourself to a lawsuit. For, as an example of a generator, I have a nice Rolls Royce here, 1200 kilowatt standby emergency generator on a project that I'm working on in Miami. So I'm hoping that once they install this and I go and measure, I have finally a project that's at the design stage and not after the fact. But in this case, what we did is they do have on the two standby generators. One is bigger, one is smaller. The smaller one is 6 kilowatts. But even though these are not as big as they get, you could tell that at 1 meter out of the louver, they are at 107 decibels. So still, you could damage the ear permanently within a couple minutes at these levels. The placement of this new building is obviously in a very crowded city with luxury buildings with balconies around. And what we advised for was an elbow silencer to get extra length on the radiator exhaust, and a 4 to 5 foot long inlet silencer so that these generators could operate, and especially because they test them about twice a week for half an hour. If you think about this specific job, is that it's on the 3rd floor and you're shooting 100 plus decibels or 114 decibels towards balconies, it could be very detrimental to the human ear. So in this case, if they chose to not have any treatment, as the concrete room is reverberant, or just no absorptivity, so amplify sounds, they could expect about 114 decibels coming out of that louver. So that could create or damage the ear within 30 seconds. So very important. They are not to be overlooked. By the time this gets to you, engineers or contractor, it's likely too late because you don't have enough room. They only give you room for a 12-inch louver and they expect miracles. But set expectations now that you have some information in your back pocket. In this specific case, at the design stage, I sized a couple of silencers for the radiator exhaust. We lined 70% of the concrete room with wall mount acoustical panels and also added 4-foot long silencers to get to 65 dBA at the nearest line of sight, which by the code in that specific BC city area was acceptable. I schedule with the minimum pieces of information for the silencers can be done at the design stage for both the inlet and discharge, including insertion loss per octave band, ideal tested pressure drop, and installed pressure drop with system effects. So very important. The installed pressure drop has to do a lot with the setup and close proximity with other duct elements. So all that can be simulated in the same software that I was showing you initially to do the barrier wall. That's a free software to be able to size the silencers and see what the sound pressure level will be at a particular line of sight. Those acoustical panels lining 70% of the room are very important, mainly because they will prevent that sound amplification within the room, especially on those hard corners. A 4-inch thick panel covering 70% of the room could easily boost your performance overall as it travels through different paths towards the openings within the room, up to 7 decibels of added attenuation. So what that means is when you add absorptivity, you can now start using a little bit of your distance effect to the openings. We do a good job at giving you the panel layout so that you know where you can add conduit, where the openings can be, but this is just a quick example of the typical connection details where you could start adding wall mount panels into a very noisy generator room to start with. So if it's a retrofit application, the first step would be to add absorption to the walls. This is the typical solution aside from the combustion exhaust muffler that typically comes in already sized by the generator manufacturer. You have your silencers for air to come in so that these diesel generators can operate, so they can combust and then start generating power. You also have your radiator fan, your radiator exhaust to cool off the system. That is typically where you're going to use most of your pressure drop or the total static this system or this unit can take, mainly because you don't have such you don't have a lot of room to change the sizing and transition so abruptly into the louvers. So a lot of that available back pressure that you have to play with is going to be used at the radiator exhaust. So just remember that as you're designing for solutions on it. The transitions and the connections from the generator to the silencer here, and from the silencer to the louver, that's also double wall. In the scenario where they don't want to use wall mount panels for cost savings, and you're amplifying noise within the room, you don't want all that sound to echo around, get amplified, bypass the silencer, break into thin sheet metal, and then out goes through the louver, creating issues. So in order to avoid bypassing the discharge silencer, you want to make sure that those transitions are double wall, and you are able to insert your dampers. In the case of the inlet penthouse that we also are able to size, you could have some filters. All that can be customized to a particular application. A few guidelines for you that I want to share, and I know this is long, guys. Thanks for bearing with me. Hopefully Tom got you lunch, but if you can stay focused for a little.
I would not be. I'm. I'll just speak for myself. This is probably more content than I would have ever imagined you could come up with for a 4-inch acoustical panel. I mean, there's a lot of content here, so I'm enjoying it. If no one else is, fine, but I think it's really good, and it
Okay.
certainly points out a big industry issue where do you turn for a problem like this? Because usually you're just buying panels and silencers and trying to tinker toy them together instead of having sort of a complete solution for a challenging problem. So you just keep on going, Mauricio.
Excellent. I just wanted people to hear your voice for a little bit, just to make it a little
You
bit
think they
more
missed me?
interactive.
I really doubt
I
it.
I
Okay.
think so. But thank you, Tom. Those are good points. So as we continue with this, at least the minimum design guidelines I want to give you, at least for the inlet, is that opening. You have a lot more play on the opening to bring air into that generator, electrical mechanical room. So as long as you size that silencer and the louver to have a phase velocity to not exceed 350 feet per minute, you can keep your pressure drop really low. At the radiator exhaust, you do want to add at least a 2 to 3 foot long transition from the silencer to the louver. The reason being is if you look at this velocity profile come out of a CFD analysis, is even though the airflow is coming out at a nice 900 feet per minute from the radiator exhaust fan into the silencer internals, from any manufacturer, the largest free area you're going to get is around 50%. And that's going to give you your best pressure drop. The largest the free area, the better the pressure drop inside the silencer. But because it's a 50% free area, what does that do to your airflow speed? It doubles it at the very least. Therefore, that transition from the silencer to the louver had to at least be 2 times the one of the dimensions of the silencer. So you're going to have to transition if the silencer is, I want to say 10 feet wide, your opening at the louver is going to have to be on the width at least 20 feet so that you can properly transition, slowing down the air. Otherwise, you're going to ram about 15 to 1800 feet per minute right into the louvers, choking the system, making it so that the generator cannot operate. A couple of pictures of some installed applications. You can see right here that in this case, they decided to transition before they went into the silencer so that after the silencer, they have a longer transition to slow down the air. In this case, once it exited, it was about 1,000 feet per minute, leaving the silencer. Also showcasing that the opening at the top has silencers on the vertical because you're trying to treat all the lines of sights, not just one. They did add wall mount 4-inch acoustical panels. These panels are not just flimsy panels. You can cut them on site. We could give you a specific openings if need be, but you're able to add conduit on them. They have stiffeners every 16 or every 12 inches. 12 inches if you're going to walk on them, so that you're able to add a lot of the things that you need to hang, such as lighting, conduit, alarm systems, you name it. So just as a general piece of information, these panels will be robust and it will give you that extra 10 decibels of reduction overall in your system. At the inlet, here is a quick pressure analysis here showing that as long as you keep your phase velocity very low, if you think about 120 decibels inside the room and knowing that your 32 hertz, your 63 hertz, the wavelength of that is 18 foot wide, you're going to have to use something a lot wider than just a 6-inch, 8-inch acoustical louver, because otherwise that 18-foot wave is just going to go right through. So these silencer, at the very least, they range from 3 to 5 feet. It's going to impede the transfer of that wave more effectively. But for that, you also have to close the air gap a lot. And if you're going to close the air gap to the degree that you have a low pressure drop, then your opening needs to be very big. So for that to be an ideal condition, so that your pressure drop doesn't double, that's where I try to give you the guideline of not exceeding that 300 feet per minute phase velocity into the silencer or the louver. If you do that, you rest assured that you're not going to run into troubles with pressure drop. This is another velocity vector profile showing you how the air comes in from the outside into the room. And although it speeds up very shortly after because of the size of the opening, it's going to slow down, keeping that pressure drop at 0.05 inches of water gauge. And that is important because if all of a sudden that was a quarter of an inch, imagine the people that might have to leave the building through that room, and all of a sudden you have negative pressure. So the radiator exhaust is ducted, so that's separate. That's not going to affect the room. But if all of a sudden you pressurize a room with a quarter of an inch, a third of an inch, and somebody's trying to leave the room during an emergency, and you're not able to open the door, that's going to be big problem. So, another reason why paying attention to the size of these comes in handy, even as people might try to exit through the doors of that space. So a couple of pictures of an installation of an outsider plenum. You can see how big the openings are. We use the, obviously tested data, CFD analysis to really see the impact on this silencers into the system. But as they are installing them, you could see that the opening is fairly large relative to even the size of the generator itself. So this is the level of detail you would get working with a reputable manufacturer. This is the radiator exhaust, and as you could see right there, you're using a quarter of an inch of back pressure from a total of a half an inch that that generator can overcome. That is why at the inlet you have to have such a large opening so that you could reduce your pressure drop. In this case, because the airflow was 207, I guess the airflow was in such a way that the opening allowed for the phase velocity going through the silencer and louver was under 300 feet per minute. The pressure drop wasn't a tenth of an inch. Looking at the previous CFD was more 0.05, allowing for the rest of the pressure the generator can account for to be used for your dampers, for your louvers, or any other element on the way. You start seeing now a common approach on all these solutions. It starts by using accurate tested data, using the right calculations or reputable softwares to ensure that you can effectively size the length, width, and height of your silencers. You see the added service of really predicting what the impact on performance is going to be by adding silencers or barrier walls or acoustical panels on the way of airflow. And just to reiterate, a lot of specs, even for outsider plenums, I see a lot of shortcuts saying it needs to be self-supporting. When you get to the size of these openings, size of these solutions, and you're attaching to a massive building, and you have a pressure rating, you have a wind load, you have seismic, there is no such a thing as self-supporting. You're going to have to spend some money, whether within your office or through manufacturer that has capability to do it, to see how to properly support under given loads based on a particular jurisdiction or area. So they go hand in hand. As simple as these insulated boxes may look like, there's a lot that goes into it to get the right acoustical level, get the right airflow into the space for optimal operation of the equipment, as well as looking at your structural support to prevent failure of components collapsing. We're going to move on now into seeing how we apply all this scientific approach into other noise control solutions. Another way you could use acoustical panels is to use them as the casing of the built-up air handling unit. In many cases, you already have existing mechanical rooms in the third floor, fifth floor, and you cannot bring a new unit. So you got to bring your filter bank, your fan bank, your coil section all in pieces and replace everything at the mechanical room, because these specific air handling units run at either 6 inches or 10 inches of pressure. Then you're going to have to look at the structural as well as possibly as a terminally broken construction, depending on the parameters that you have. This is how they look like. As you could imagine, there is not such a thing as zero fasteners when you're getting to this size. Eventually, you're going to have to support it. So if you see manufacturers out there saying, hey, this is self-supporting and this 80-foot wide by 40-foot tall plenum is just going to fly alone in the air, it's not such a thing. You're going to have to, at some point, support them properly. In this specific case, this is a top secret facility in Denver for a government building. You can see the panel layout. You can see that the fan room sections have perforated liner inside. Why? Because you're trying to attenuate sound right at the source. The main source within an air handling unit is obviously your return fans or your supply fans. So adding perforated metal there will result into a quieter discharge sound power level of the unit. The rest of the assembly is a solid construction. You're trying to block, maintain temperature, but also in the coil section, if you experience condensation internally, you don't want to have that perforated metal exposed over a long period of time. These are typical connection details because this specific project, which I cannot name, the project name for it was rated up to 6 inches of positive or negative pressure. It required structural support, and we were able to supply that ahead of time to have a successful installation overall. So just another example on how to use acoustical panels, and we're going to need all the details: what equipment you're going to put in, what type of fans you're going to put in, what's the weight of the fans, how do you want us to tie into the structure? Do you need openings, pre-cut openings for conduit, or do you want to cut them on site? There is many ways to do this, but we're more than capable to do so. And again, you're going to use either a 2, 4, or 6 inch acoustical panel based on the pressure rating you need to design for. As I mentioned at the beginning, and based on Tom's good questions, the case studies that we have are after the fact applications. In this case, this is Jefferson Middle School. It changed names due to the lawsuit, but a lot of people were complaining, especially in summer when the unit kicked in at full and the remote condenser started pumping noise. Even though it wasn't a roof far away, it was being disturbing to residents, especially when they were trying to sleep. In this specific jurisdiction, they had a very tight sound pressure level requirement. So when you look at this picture here, video, I'm hoping it's not super dark. If it's super dark, Tom, I'm sorry, we did test this. But you could see after we installed the barrier wall, and I'm here with the contractor, the acoustical consultant, and the rep, and I'm measuring sound at several different points and several different distances to corroborate that our barrier wall, additional to our remote condenser enclosure, was indeed providing enough attenuation, specifically across the street where they had residents trying to sleep on the third level. When the unit kicked in, sound levels at the windows where people were trying to sleep at night were 17 dBc above background. And you'll notice that I say dBc, which means they didn't use the A weighting to massage low frequency performance. Because even when you're sleeping at a certain level, low frequency could be disturbing to you, that might increase your heart rate, can be unhealthy for you. So at some point, go ahead.
Maybe so, we've been working together for a long time, but it wasn't always that price sort of included the structural offering along with panels and silencers. If you have time, maybe you could talk about that. I think it was sort of a demand thing more than anything, but 10 years ago, I could send a bunch of panels and silencers out to the field. They could put it together, and it would probably be a big mess, and we wouldn't necessarily solve the sound problem. Any thoughts on that?
Yeah, so I mean, you could try to buy lock, and I do hear a lot of feedback. Hey, I'm just using that 12 gauge screen wall at the back, and I insulate some sections. And sure, depending on the distance and equipment around, it might work and you might get lucky. But once you're dealing with a complaint, yes, you have to do the engineering for it. There is no shortcut, proper engineering practice. And now in this case, the cost of this solution was 4 times higher than it would have been if they did this at the design stage, because they did have to reinforce the structure, add structural after the fact as well when you look at the frame here. So it doesn't get pretty when it's after the fact. You may think you're saving money initially by value engineering out all the noise control products, but especially when you're close to residential, schools, high learning spaces, performance arts, and when people are trying to sleep, you just want to be careful. And it's not hard to analyze this. Like if you start playing with our software, or if you want to give us a few jobs just to experience and get your feet wet to see what it takes to come up with this, it doesn't take a long time to give you a budget of how much it would cost at the design stage. But rest assured, it's going to be, if not, if not twice, at least 4 times more expensive when it's after the fact. Hopefully that answers your question, Tom.
I was just more thinking along the lines of, the reason that the rooftop equipment is on the roof is because someone else did a budget somewhere down the line. So if you're doing cost reduction by moving the equipment onto the roof, fine. Before you give all that all that money back to the project, take into consideration what the acoustical issues are going to be before you give the full VE back to the architect. That's what I'd say.
Good point. Yeah. So yeah, I mean, there is a way, and then we can give you that budget very quickly. Just have in mind that it does involve, with any enclosure, indoor or outdoors, and especially when it's exposed such as this, it will involve a structural analysis, perhaps some CFD, and an acoustical analysis at the very least to properly size that. And although we do offer a free service for acoustic analysis, the structural analysis or CFD analysis is at added cost. Now I'm going to hand it off to Serem to talk about some other solutions. Serem, back to you.
Thank you, Mauricio. Okay. So the first one we want to discuss is this job out in Colorado where they needed to have an outdoor vestibule. So they did have some equipment they wanted to install right on the outside.
You're not sharing your screen yet.
Oh,
There you go.
okay, perfect. Okay, so this job was out in Colorado. They needed an outdoor vestibule to store some equipment out here close to a built-up air handling unit. One requirement they had for this was that they wanted to be able to do maintenance to the coils. So they did have some coils, heating coils, cooling coils that they wanted to be able to pull out. So the design consideration here was, is there a way for us to access our equipment here without having a cumbersome process? But if we ever needed to pull our coils, we should still be able to do that. Well, we went ahead to design this enclosure for them where they did have the access door for man access. And if they ever needed to pull the coils, they could take out this entire front face. So these are removable panels that allows them to do a complete pull from the side of the built-up unit all the way outside for their maintenance. This is what it looks like before, and this is what it looks like after. So we do have the pictures here. We do make sure that it was painted to match what the built-up originally had. They are able to man access through here, and we have the bolt-on design where they could pull out this entire front face if they needed to pull anything from the built-up air handling unit. The next one we do have is a pump enclosure. This needed to be outdoors. It needed to keep some of the noise coming from that, and also needed some thermal properties as well, where in the winter you did not want it to get too hot. Sorry, too cold, and in the summer you did not want it to get too warm as well. So they did have this pump enclosure. They could actually buy it from the manufacturer, but it was way more expensive. We came with the design, took the drawings, were able to design that, provided double doors to be able to do any maintenance on the pump skid. We also provided our 2-inch acoustic panels that were rated for STC 34, and this has been installed and is running very perfectly, fit to finish. No issues with that at all. And this is what it looked like in the workshop when they were installing it before craning it up to the roof. We did have another job where there was an ice rink where kids would play, and they had an exhaust fan that was pulling a lot of air out of that. This was getting very noisy, and I believe they were around 60 dBA for this particular space. What they needed to do was come down to 50 dBA, which would be exactly where they wanted to be for these kids. We did run our acoustic analysis because we do have the software. We ran and we figured out that most of their issues were from the radiated noise. So we provided 2-inch thick panels, STC 37. These are very customizable, so we did work around the framing that existed. We also made sure that we painted it to match and have a very good aesthetic and overall good finish. We're able to meet an 8 dBA reduction. They did have an external consultant go in, measure the sound levels before and after the installation, and they were super happy about this. So this is what it looks like before, right above in the ice rink, and this is exactly what it looks like right after the installation. We took all the drawings as is built, and we were able to provide the panels pre-cut right from factory to make sure that it was ready to install by the installing contractor right when he arrived on site. This has been installed, it's been working well. One thing that did happen was we had to look at manufacturer clearances to make sure that we were not breaching any warranties on the fan in terms of what spacing we needed to be around that exhaust fan in this scenario. Another job did come in for a high secret level military base where they had these openings on the side on the wall and they wanted to exhaust 40,000 CFM fans. So they decided 40,000. They went for 10,000 mushroom fans, each one at 83 dBA. So adding all of that up, these would be operating at 89 dBA. What was their goal? To get to 55 dBA for any worker that was standing right here and working right underneath this system. We used our acoustic analysis to determine that with the distance deductions, they would be at about 85 dBA with all these fans running at 100%. Based on that, we came up with a solution. The first one was to create a plenum space with acoustic panels. We did that using our 4-inch thick panels. This was rated to STC 46 to make sure that all the radiated noise was kept from escaping through and right into the space. The next was making sure that we used our silencers to a holistic approach to ensure that the sound levels right at the inlet of this return silencer would meet the dBA levels they were going for within the space. And yes, we were able to hit 52 dBA for a receiver right underneath this, which would be NT51. It's a hangar where they work on jet planes, so NT51 was just at about where they needed it to be for this. Now, Tom did bring up a good point where structural engineering is now becoming something that is commonly requested for and asked for. On this particular job, we did run all the FEA, we ran the structural analysis. We did have the cabs being built out of our panels. We had to internally stiffen them to make sure that they would be able to withstand all the loads, the wind loading, the lateral loading by the weights of the fan, as well as the pressure within the plenums as well. We did also provide recommendations on how they would support the silencers within the space with all this structural support that would go down all the way to the receivers. I'll pass it back to you, Mauricio.
Well, we're getting close now to the last slide with some time left for questions. But before that, one of the main hot topics lately on the many states across the US and Canada is data centers. And these big buildings that have a lot of equipment to keep those servers cool, obviously, especially the ones that are, maybe they are not using adiabatic coolers yet. But depending on where it is, if they put them in Texas, if they put them in Phoenix with very harsh environments, and you're going to need a lot of equipment plus backup power, additional to all the air handling units to bring air in to cool them off, and you have hundreds of these pieces of equipment close to residential. Those are a good example of sites that could use noise control solutions without exception. So this is a quick simplified version because we cannot share any of the details of specific projects we work on with big names for the data center world. But just looking at the slide in front of you, the typical solution is going to be what we talked about through this session, which is going to be your discharge plenum with the right spacing from an air-cooled chiller to the silencer, a very specific silencer with the lowest pressure drop possible so that you don't impact cooling performance of the chiller, and very large openings so that they can operate as well. In this specific case, even though it looks simplistic, there is a massive acoustical barrier catwalk so that the sound from the generator gets blocked with the barrier, but also what goes over can get absorbed within the catwalk and then by the silencers. All those air handling units pulling air in to condition those servers are also the sound power from them, and they just don't have one. Every set of louvers here has one of those big units. So, an entire array of about 50 silencer banks per side is what you could see behind this wall. Those servers also emit a very particular frequency that can be disruptive to residents. So the silencers and the catwalk are multi-purpose for the sound coming in from outdoor equipment into the offices in there, but also for the hot aisles on the server rooms, that high frequency noise coming through openings towards residences around. There is no quick answer, cheap solution that fits all. The cheapest solution is to do it at the design stage by using that scientific approach, using tested data, looking at the structural, CFD, and your acoustic analysis recommendations. So that leaves us, with about, I have here 16 minutes of questions, comments, concerns, or yeah, this is the time to I'll just open up the floor to questions. And Tom, I don't know if people are able to just say them out loud or if you want to read them, if you see any of them in the chat.
Just post them in Q&A and we'll read them off. There are already some good ones. You can, just because Mauricio is sharing it, you can download the acoustical analysis software. It is fairly straightforward to use, and there's a bunch of tutorials in there for helping you use it. And of course, Caleb or I will be happy to help you get started with it if you're interested. David Jones liked what he saw. Thanks, David. You crushed it, Mauricio. There's no questions. I can't believe it.
And Serem, may I ask? Yeah, may I
Of
comment
course,
too?
Anselm.
Serem did a
Of
good
course.
job, and
You did-
hopefully
no, you-
Jackson took care of all the questions that were asked during the session. That's why we don't have any questions left. But if anything comes up, you can reach out to us directly or through Tom, through Airflow. Anytime you need to get into any sort of these applications that you saw or a new one, you just ask. Just because you don't see it on the website doesn't mean we haven't done it.
could I ask you for one thing? And if people are done, they're done. But could you go back to, there was that slide where you did the analysis of different silencer standards.
Oh, yes.
That one's so fast. I think it's what you were saying there had to do with which standard you're testing to,
Yes.
but I'm not 100% sure.
Yes, that is exactly the message. So let me just open that slide. Give me a second. All right, let me know.
That's the one.
Now let me switch and go back now to this one.
Yeah. So the writing's a little bit small, but it looks like ASTM. Oops.
There it is. ASTM E477-20 is the latest standard. But it's a good point. I should just put it in writing big.
So what you're showing here is the delta between the standards of 13E and 20?
The limits, yeah, the orange light section at the above is the limit. So anybody could test in your black line, and they could massage performance to the top of the curve, the top of the limit.
To the
So
orange.
to the top of the light orange. So
Oh,
anybody could get 4 decibels off on the 63 hertz and then add another 16 to appear better.
well, every now and then we'll see a submittal that has data that's just like so far off of ours. And I wonder if that's it.
That is exactly the reason why they are tested to an older standard.
Okay.
We're not saying that our silencers are better. We're just at least telling you that if you specify under ASTM E477-20, you at least you know what you're gonna get.
Okay. Because if I'm a consulting engineer and I see ASTM E something, 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 I'm like, we're good. Versus like, oh, I need to look at the last 2 digits to know if I'm getting the right thing. So that's one of those like you just wouldn't know unless. So I
Yeah, that's
think
a very good question. Thanks for
yeah. So the
clarifying it.
takeaway is you should always trust Mauricio no matter what, and don't trust anybody else. I think is the takeaway.
Or just trust the latest standard. Because I think in general, my last comment, if there is no more questions, is we're so used to buying the top of the line phone, where when you buy a car, you don't go with a manufacturer that says, "Oh, I'm getting the engine from A, I'm getting the door from B, and I'm getting the panel from C, and all the electrical from D." And by the way, it's never been tested, but it should work okay. You will never ever do that. So I would say, as an engineer, you have all the power to bring back good engineering, even for HVAC.
Yeah. I got one last one for you. How often do installers, engineers, price get run into problems because of system effects? So they look at the silencer, they see that the pressure drop is 0.2, they put a transition in front of it. Like, does that happen all the I know our submittals address it to a certain extent, but how often is that problematic?
So typically, when we have run into installed system effects issues are in ducted solutions, where all of a sudden the transition from the bottom of the curve to the silencer is extremely drastic because they have a structural beam on the waist, and the contractor had to be, skillful around it, and we didn't know. Then all of a sudden the back pressure quadruples. But for outdoor solutions, because we're trying to follow all these guidelines of big openings, low phase velocity, we're pretty certain that we're not going to run into issues. And in the scenarios where we are not confident, we do suggest doing the next best thing, which is a CFD analysis, which is a good educated prediction.
Sure. Okay. Well, with that, I'm going to say thanks to everybody and remind you all again, you'll be receiving the typical notices in our fun format from the blog about the May road shows where you're going to see acoustic panels being assembled for an enclosure. We're going to have our thermal break panels. I think we're going to have maybe have a cutaway of a silencer so you can see the inner workings of the silencer, and food. So those you'll have to register for it, but we'll be in 13 different sites. And if you can't make any of those, let me know. We can always work around that too. So with that, Jackson and Sedem and Mauricio, great job on this presentation, and thanks so much for putting it together. You guys are all the first ones to see it, so hope you enjoyed it.
Thank you very much, everyone. Thanks,
All
Tom.
right. Thank
Till the
you.
next one. Bye.
All right. Till the next
Thank
one.
you.
All right. Bye.